we're going to discuss the logarithmic function. So the best way to introduce the logarithmic function is as follows. We computed powers by knowing the base and the exponent. So now imagine that we have a situation where we want to guess what exponent yields a certain power, meaning we ask to what exponent, to what power is equal to 16. And of course, we know that the answer to this question is 4. Or let's say we ask 3 to what power is equal to 1 over 27. I hope that the moment's thought here can suggest that the answer is -3. In the two cases, we can say that the answer is the logarithm with base 2 of the number 16. So we take the power, we take the base, and the exponent to which we need to raise the base in order to get the specific power is the logarithm. So here, the answer, the -3 that we found, will be the logarithm with base 3 of 1 over 27. So more generally, if we ask a to what power is equal to x, then the answer to that question is the logarithm with base a of x. So we can be quite specific here, and we can say that if a is greater than 0, a is different from 1, so this is something that we actually need now, a fixed base, then the logarithm with base a of x is defined as the exponent to which we should raise a in order to obtain x. In other words, maybe the most direct way to express this is that if we take a and we raise it to its logarithm with base a of x, okay, this exponent is specifically designed so that we can get x. Or you could even say that the logarithm with base a of a to the x, so to what exponent do we need to raise a in order to get a to the x? The answer is x. Sometimes these two relations are referred to in elementary mathematics as the round-trip theorem. They pretty much establish the fact that the logarithm with base a and the exponential function with base a are inverses of each other. They do pretty much opposite jobs. So you take what the input in a certain situation. So if you have a situation in which you have the input and the output of one function, then those will become conversely the output and the input of the other function. So in other words, what I'm saying here is that if you take 2 to the third, you get 8. So you see 3 gives you 8. If you do that for the logarithmic function with base 2, and you get that the logarithm with base 2 of 8 is equal to 3. So you see here 8 gives you 3. So 3 gives you 8 in the exponential function, 8 gives you 3 in the logarithmic function. So they go, one pretty much complements the other. Now, what are the properties of the logarithm. So to look at the properties of the logarithm, it would be a good idea to juxtapose them to the properties of the exponential function. So the exponential function satisfies the properties that we mentioned before. A to the x plus y is equal to a to the x times a to the y. And a to the x all raised to the y power is a to the xy. And we could also notice here that a to the 0 power is equal to 1, and a to the negative x is 1 over a to the x. These are things that we saw in the case of the exponential function. So these properties have their analogs for the logarithmic function. So the logarithm with base a of x times y is equal to the logarithm with base a of x plus the logarithm with base a of y. And the logarithm with base a of x to the y is y times the logarithm with base a of x. And the logarithm with base a of 1 is 0. And finally, the logarithm with base a of 1 over x is minus the logarithm with base a of x. So these are the properties, the main properties of the logarithmic function. And from all those properties, the one property that we're going to use in some very interesting places is this property right here. Okay, this is the one property that we will see will become very, very useful during our course. Now, why don't we compute a few logarithms just to see how this works again? So we have the logarithm with base 3 of 81, the logarithm with base 4 of 1 over 64, the logarithm with base 5 of 1, the logarithm with base 3 of the 4th root of 3. Let's compute this logarithm. So please pause the video and try to compute these logarithms based on asking the right questions, meaning, for example, you want the logarithm with base 3 of 81, ask 3 to what power is 81? The answer to that question will be the logarithm, and so on. Try to do this in these 4 cases. So please pause the video. I'm going to wait for a couple of seconds. Let's give the answers. Okay, so again, you can ask 3 to what power is equal to 81, and the answer is the 4th power, so this will be 4. Now, 4 to what power is equal to 1 over 64? You know that in order to get 64, you need to multiply 4 by itself 3 times. To get it on the denominator, you need an extra negative sign. So here the answer will be negative 3. The logarithm with base 5 of 1, the logarithm of 1 with respect to any bases is 0, because 5 to the 0 power is equal to 1. And this one is rather interesting, the last one. It's just a matter of definition, because remember that 4th root of 3 is the same as 3 to the 1/4. So you can see right away that if you ask to what power you should raise 3 in order to get 3 to the 1/4, I mean, the answer is pretty much 1/4. Okay, and these are a few examples of how to use the logarithmic function. Again, we could ask what is the most interesting base for the logarithms. And here, we actually have also the base 10. So when we use the base 10 in sciences, not in mathematics, there's a very interesting thing that happens here in mathematics. In sciences, usually when we write logarithm with base 10, we just simply write it as logarithm. And in some sense, the logarithm with base 10 of a number is pretty much the number, especially for a big number, is close to the number of digits that the number has. But maybe the most important logarithm is similarly to the case of the exponential function. It's a logarithm with base e. And we have a very special symbol for it. We denote it by ln, which stands for the initials of natural logarithm, but the other way around in Latin. Okay, so you could ask, of course, if the base is z, what are the numbers for which we can easily find their logarithms? And I guess we might get a little disappointed here because the numbers in every setup, the numbers for which you have simple logarithms for a given base are exactly the powers of that base. So for example, you can say that the ln of e is 1, because if you ask e to what power is e, obviously the answer here is e to the first power is e. You can say that ln of 1 is 0 because the logarithm of the number 1, no matter what the base is 0. But other than that, if you want much more, you should go to powers of e, which doesn't make it that spectacular. So ln of e squared is 2, for example, or ln of the cubed root of e is going to be 1/3. So in general, the round trip theorems for the case of the natural logarithm is that ln of e to the x is x, and e to the ln of x is x, which are the two relations that can be thought of as defining, each one of them actually defines the natural logarithm. One of the things that I want you to understand, one of the reasons why we use the natural logarithm so much, the truth is that we could use any one specific logarithm that we like, but the bottom line is that any logarithm can be expressed very easily in terms of the natural logarithm or in terms of any other one logarithm that one would choose. To make a long story short, if you want to take the logarithm with base a of x, it turns out that this is precisely ln of x over ln of a. That tells you precisely how you can use the natural logarithm in order to express all other logarithms. And pretty much in sciences, we do use the natural logarithm most often, more often than anything else. In fact, in theoretical mathematics, that's the only logarithm that people essentially use or classically used. And that's why in theoretical mathematics, we don't even use the notation ln, just denoted by log. But that's it. And that's the end of our discussion of logarithms. Thank you for watching.